It's our pleasure to have one of our very own, Professor Dmitry Korotkin from Concordia University. And he will tell us today about tau functions. And there's an interesting word in the title, symplectomorphism, which I've never heard, but we'll learn more about this today. So it's your, the floor is yours.
Yeah, okay, so thanks a lot. So thanks for attending, and it's my pleasure to present our joint work with mainly with Marco Bertola, and one of the papers is still in progress together also with Fabrizio. So that's the title, and I'm going to explain a little bit what all of that means. So the idea was, our original motivation was to look at isomonodromic tau function and to understand how to define properly its dependence on monodromy variables, because of course Jimbo-Miwa equations tell us how tau function depends on isomonodromic times, but how it depends on monodromy variables is a big question mark. And for that, the guiding principle for us was to use the symplectomorphism, the term which seems to be a bit surprising, but it's there is the map, the monodromy map for Fuchsian equation is symplectic. So, and then such a map admits the generating function, and the idea was to try to identify it with the isomonodromic tau function, including dependence on monodromy variables. So that's the rough idea. Now, the talk will consist of three big parts. The first part is somehow technical, but still it might be of interest to some people, namely how to, looking at Goldman bracket on the character variety. And here I don't restrict myself to genus 0. First of all, how to write good coordinates for this Goldman bracket. And the good coordinates are somehow known for quite a while now. These are Fock-Goncharov coordinates. In 2×2, we have also Fenhill-Nielsen, but Fock-Goncharovs are much more superior to them in various respects. So the question is how to write the symplectic form in these coordinates. This is technicality, and this technicality we need because we want to integrate the Goldman symplectic form. And for that, we need to find some symplectic potential. Then we apply that to the theory of tau function here. And then these two last points, this applies to WKB expansion. And we do it in two contexts. First is the Riemann surface, the second order equation on the Riemann surface, so OPER, and the generating function, the monodromy map for that was introduced in physics context by Rosley, Nekrasov, Shatashvili, called Yang-Yang generating function. Well, of course, with various details. So we look at WKB expansion of that. So these three results are published. This paper number 4 is in quasi-ready state and a bit in preparation. How that applies to how to properly do WKB on Fuchsian systems. So this is roughly the topics. I'm going to start describing this, and I'm going to skip some details, which you will see on my slides. If there are questions, I can provide additional explanations. So this is the subject of the first paper. It has nothing to do yet with the monodromy map. It's just completely about Goldman bracket. So that's the Goldman bracket. We look at Riemann surface of genus G with certain number of punctures, look at fundamental group, look at the character variety, say SLN. Our main example will be SL2 or PSL2. But still, we can do it in SLN. And then Goldman bracket looks like that. The good variables on the character variety are traces of monodromy. Is good in some sense. In some sense, they're not as good as we would like to, but these are natural coordinates. And then the bracket between traces of two monodromies along loops gamma and gamma tilde is this sum, where what we do is from these loops gamma and gamma tilde, we look at the intersection points, and each intersection point gets resolved. We get a new contour. Look at monodromy along this, well, loop, right? And its trace. And this new gives the contribution of this intersection point P to the intersection index of these loops gamma and gamma tilde. So classical result, Goldman bracket. In PSL2 case, it's the same as Weil-Peterson Poisson bracket in PSL2R case. Okay, so let's look at choose some standard set of generators. Here a little bit non-canonical choice of alpha beta generators, but there is some technical reason for that. And that implies the corresponding relation between monodromies, because we assume that the monodromy map is a homomorphism of pi1 to SLN. And we are going to look at the submanifold of the character variety where all monodromies are diagonalizable. So this is the Poisson bracket. The first question is, okay, great. Poisson bracket is here. Where is the symplectic form? Well, first of all, this bracket is degenerate, which, well, these traces of monodromies around punctures are Casimirs. So we can hope to invert this bracket on a symplectic leaf. So how to do that? Well, there is some paper of Alexeyev and Malkin, which was written in 1995, 26 years ago. And the result looks is a bit discouraging. You see this, in principle, result is there, right? These M's, M1, Mj are monodromies around punctures. There are monodromies around, well, ALs and BLs are monodromies around alpha and beta cycles. Then one cooks various expressions here and cooks this form. So the structure looks a bit scary, but we are going to explain where this structure comes from. There is nothing very, it's actually more or less natural. So that's the classical, well, 26 years old result of Alexeyev-Malkin. And the statement is that this form is the inversion of the Goldman bracket on the symplectic leaf. Right, so, okay, now the goal is, yeah, still, if you look at this one, the question is, since the symplectic form is closed, we know that there should locally exist a symplectic potential. It should be one form such that differential of this one form is equal to this two form. If you look at this expression, there is no way you can figure this out. And what helps is the link to Fock-Goncharov. So how does that work? Before explaining that, let's introduce also another convenient space, which was introduced probably first by L.Jeffrey in '94. And this space looks like that. Its monodromies around along alpha and beta cycles are the same, and monodromies along these small loops around punctures, we look at not only the monodromy itself, but also its diagonalization. Lambda is the diagonal form of the monodromy, C is vectors, matrices of eigenvectors. And so essentially what do we add? We add the variables which normalize the eigenvectors of the local monodromies around punctures, right? And then the natural form on this bigger space is some of the Goldman form on the leaf and an additional piece. So essentially, you introduce partners, canonical partners to Casimirs, to the eigenvalues of monodromies. And then it turns out that this combination is already the non-degenerate form, closed form on the whole space M hat, right? You extend the symplectic form from the leaf to the whole space, but it's the space M hat, extended space. Okay, so it's convenient to parameterize the matrices of eigenvalues of local monodromies in terms of these M's, because the determinant is 1, so it's convenient to introduce these M smalls such that the eigenvalues look like that. Okay, so these are some technicalities. Now, the main theorem of the first part of the talk is the following. Let's introduce the logarithms of Fock-Goncharov coordinates, which I didn't introduce yet. And let's introduce this. So m's eigenvalues of these matrices lambdas, and rhos, these additional variables, you can look at them as normalization factors for the eigenvectors of the local monodromies. And sigmas are logarithms of Fock-Goncharov variables, right? This is pretty tentative formulation because, well, I don't want to be very technical at this point. So then the statement is that this is the extension, well, the form W, which I have written before, sum of Alexeyev-Malkin form and plus additional piece, which makes it the form on the whole extended space, that this form is non-degenerate. And if you restrict it on the symplectic leaf, then you forget about this piece. Sigmas, of course, become dependent then, but still, well, and these n's are just integer numbers. So essentially, sigmas are almost canonical variables for the Goldman form, right? And I'm going to tell a little bit more how to define sigmas, how to compute these n's explicitly, and then, so the corollary of this statement for the extended space is this, right? So the Goldman symplectic form, this Alexeyev-Malkin, this big expression can be neatly written in terms of Fock-Goncharov coordinates like that, right? So the statement looks easy. The computations, this n's, is not so easy, but what we needed is that this object and that object also can be very efficiently integrated explicitly. You just take, for example, sum of, forget about this d, and this is the symplectic potential. Okay, so I briefly outlined the idea of the proof of this statement, not spending too much details because probably here people would be more interested in discussion of the tau function. But still, I want to discuss this main technical tool. The main technical tool is this form. If I have a graph on a Riemann surface, right, then on each edge of the graph, we can associate the jump matrix. So essentially, we are thinking of a Riemann-Hilbert problem on a Riemann surface, which is equivalent to defining a flat connection on the dual graph, because if on the graph on the edge of my original graph sigma, I have the jump matrix, it's the same as if I look at the dual graph, it's the same as the transport matrix along the edge of the dual graph. Now, the flatness condition here, it's assumed that for all the vertices of the graph, product of jump matrices along the edges coming to this vertex is 1, right? So this is the condition which can be naturally interpreted as the flatness condition of the connection of the dual graph. And then once we have this connection, matrices associated to each vertex, then we do the following. To each vertex of the graph, we associate a cilium, so which allows to count the edges counterclockwise starting from some position. So for vertex V, this is the double sum of all edges coming to this vertex, right? And they are ordered, so this denotes the ordering of the edges. And then we have sum of traces of these products, right? So it's essentially double sum, and V runs through all vertices. Now, of course, if the vertex is one valent, then we don't assume any condition. And in practical implementations of this one edge vertices, one valent vertices are going to be important. So this kind of form, I don't know where it appeared first. I know that Marco was studying this type of objects for 10, 15 years. So here they turned out to be quite useful. Okay, so that's the main technical tool. And now what's good about this form is that it's invariant under the standard moves. If I have natural, if I merge two vertices with natural transformation of the jump matrices, the form remains invariant. If I merge two edges outgoing, well, having two vertices in common, glue them together with natural transformation of jump matrices, the form remains invariant. The phase contraction form remains invariant. So this form is nice, it's invariant under various graph transformations. Now, how it's useful in our computations? Well, if we look at this huge Alexeyev-Malkin expression, it turns out that it has a natural interpretation. We take this standard form and apply it to this kind of graph. So this is the, these are the punctures, right? And the monodromies, so this is monodromy along alpha cycle, this is monodromy along beta, no, this is alpha cycle, this is beta cycle. So some monodromies we split into this P, there were these matrices P's and D's in Alexeyev-Malkin expression. So basically there is a graph underlying the expression, and inserting this graph into the standard form, you get the inversion of the Goldman form. Now, then, of course, by graph contractions, you can just translate it into the standard graph like that. Beta cycle, alpha cycle. You see, well, one just merges these 2 points, then one merges these 2 edges, and one comes to this graph. Right, so, and then one gets, and another way to get this standard graph is to come to it through Fock-Goncharov construction, which looks as follows. So I stated here. Now, Fock-Goncharov graph. This is probably not known to everybody here, so I'm going to discuss it a little bit, the nature of Fock-Goncharov variables. So one looks at triangulation of the Riemann surface. These black edges form the triangulation. Then to these black edges, we pick inside of each triangle, we pick the central point. Everything is topological, so who cares where it is? And add those red edges. And on top of that, one adds these blue objects, which we call cherries, right? And you see there are inside, there are these one-valent vertices. One-valent vertices are exactly those T's, the punctures. You see, the punctures are in one-to-one correspondence to the vertices of the triangulation. They're next to them, but they don't coincide with them. So that's the main graph. Now, how to describe the jump matrices? Well, to those edges, one associates the, well, in 2 by 2, these are just off-diagonal matrices. And in n by n, these are long off-diagonal matrices, and the entries are parameterized by these zeta variables. On those red edges, the jump matrices in 2 by 2, just a second, something happened. Okay, never mind, I don't know how to remove this blue. Let's just, don't want to spend my time on that. On these red edges, one introduces the matrices, which in 2 by 2 case, it's this. So there are no variables sitting there. There are no variables associated to these points in 2 by 2. In 3 by 3, there is one variable x corresponding to each point P, right? And this matrix also satisfies the relation a cube equals 1. You see, what is a cube equals 1? It's just condition of triviality of monodromy around this point. Now, in SL4, and you see all of those matrices have this off diagonal upper triangular structure, right? In 4 by 4, it's like that. And you see, in 2 by 2 and 3 by 3, the jump matrices on all three edges are the same. In 4 by 4, they're different, but still their product is 1. This is the example how this matrix looks in terms of in 4 by 4. And then each face has 3 variables associated, 3 Fock-Goncharov variables in SL4. So in SL2, there are no face variables. In SL3, there is 1 face variable for each face. And in SL4, there are 3. And then there is the description of other monodromies on this graph, right? On cherries, you have the eigenvector matrices. Then on the stems, the matrices are triangular local monodromies. So there are some details otherwise, in other words, and I'm not going to go through all of them. It's all in the archive, so, and pretty technical, so I'm not going to go through these details. What's important is the important ingredient of the final answer is this inverse of the Cartan matrix of SLN, which looks like that, right? And having this matrix G, one can write the answer, which is, you see, the most non-trivial part here is to compute the contribution of the center of each face in terms of the face variables. And this part is absent in SL2, it's absent in SL3. It starts from SL4, right? Heaviside is this function. So basically, these variables are labeled by 3 integers such that the sum is n. And you write this expression, which, well, in SL4 is the first non-trivial case. It's like that. It's pretty easy. In higher n, it's also easy, but not too much, right? And then contribution of vertices V, where red edges start talking to black edges. The zeta variables talk to psi variables, and zeta to zeta, and psi to psi a little bit. Anyway, all these expressions involve this inverse Cartan matrix, and that looks scary, but actual computation of that is easy because everything is either upper or lower triangle. I'm not, again, the algebraic details are probably not very important here, but in the end, we get the contribution of sum of contributions of vertices, sum of contribution of faces, and plus these mu's are logarithms of eigenvalues essentially, and rhos are normalization variables for the eigenvectors. Right? So that's the idea is that one can compute all of that pretty efficiently. There is no, and in SL2 everything becomes really easy. So this extended Goldman form looks like that. Psi variables are absent. There are only zeta variables sitting on the edges of the black graph and on the black edges of the graph. And there is this combination. In SL2 case, this was published almost simultaneously with us, just 1 year ago by Leonid-Chekhov. So he proved this expression independently, right? For us, it's just a special case where everything can be done very efficiently. And the corresponding Poisson tensor, well, so the question is now how the Poisson bracket itself looks in terms of Fock-Goncharov variables. And this, although various people tell that it was kind of understood at the time of Fock and Goncharov, it was not stated explicitly. They never stated that their Poisson bracket coincides with Goldman, but it does, and at least in SL2, in SL3. In SLN, people claim that this is a theorem, but we didn't find an explicit clear proof, although we have verified that, including Maple in 4 by 4 and 5 by 5, but I don't think the general proof is very clearly written somewhere. Anyway, in SL2, the Poisson tensor correspond, well, this is just a Goldman Poisson tensor on the symplectic leaf, right? And you see here you sum over the faces, all faces of the original triangulation. And in the symplectic form, you sum all, or here you sum all vertices. So it's a different story. And similar expressions were written by Penner, but in different coordinates and different context. Anyway, here it's quite interesting that you write this and that, and these matrices are essentially inverse to each other. Quite a non-trivial thing. For SLN to say what all that means, one has to use this Quiver language and write a Quiver associated to the triangulation, and then also put the variables at the vertices of the Quiver, and this arrow tells, let's say, the Poisson bracket between this and that is 1, and so on, right? And so if you just ignore these red edges, what you get is the Poisson structure for the Goldman bracket itself. If you add these red edges, then you get the extended one, right? And so that's I'm saying that it has very natural graphical interpretation, but our goal was a little bit pragmatic, right? All this formalism was needed just to be able to integrate the Goldman form. And once you have this written in terms of Fock-Goncharov variables with constant coefficients, then of course the integration is pretty straightforward. For example, you can pick this one, right? For the extended thing, and then you can ask yourself, okay, so you have the two form, you have this symplectic potential, so you have a chance to construct a natural line bundle, having in mind that these two forms should be the first Chern class of this line bundle, assuming that the manifold is good, assuming that everything is. And indeed, you can do it. For example, if you start covering your character variety by the cells corresponding to different triangulations, and you ask yourself, so you flip an edge from one and go from one triangulation to the other, how this symplectic potential changes, and the result should somehow give in the ideal world the transition function of the corresponding line bundle. Well, transformation looks as follows. The generating function of this jump, if you like, it's also the generating function of the corresponding symplectomorphism, is given by the Rogers logarithm of the Fock-Goncharov variable, essentially sitting on the edge which you flip. And then if you want to say in PSL2R, you can do things pretty explicitly when you are dealing with Weil-Petersen bracket and its extension to the punctured Riemann surface. Then you can do things explicitly. You have 5-term relation for the logarithm, which guarantees the cocycle condition with respect to the pentagon move. Then you have the 2-term relation, which guarantees the cocycle condition for 2 subsequent flips. So there is quite some extension in that direction, where you can start thinking about the line bundles associated to Goldman bracket, but my goal is different. At the moment, my goal is to apply this to the tau function. So the tau function appears in this context. You take the matrix linear system, Fuchsian system, the singularities here are simple. You assume that the thing is non-resonant, which means that, well, the asymptotics of psi near TJs doesn't contain any logarithms and looks like that. Then in terms of these, so you see this is singular term, those C's are the same C's, these are essentially eigenvectors of monodromies around these points. And A's, well, these residues can be written like that. The monodromies, well, A's are expressed in terms of those G's, and the diagonal matrices L's, which are here. L's contain eigenvalues of A's, and the monodromy matrices are defined in terms of exponents of L's, and the eigenvectors of monodromies are given by those guys. So that's the setup here. Let's see now the monodromy map. Well, so now what is the monodromy map? Monodromy map is having A's and T's to compute the monodromies, right? And there is a Riemann-Hilbert problem, having T's and M's compute A's, right? So the inverse and direct scattering problem, if you like. Now, actually, there are two versions of the monodromy map here. The first is the most naive, from A's to go to M's and L's, and slightly more refined from the set of G's and L's. So here we fix not only A's, but we normalize the eigenvectors. And then we also normalize the eigenvectors of monodromies. Now, this is the analog of this L.Jeffrey space. No, this is the analog of the L.Jeffrey space. And this A is just the space of eigenvalues and eigenvectors of the residues. And then we look at, and there is some equivalence relation here, which by simultaneous conjugation, kind of technicality. And then this tilde means that we add the positions of singularities. So essentially, the monodromy map is from A tilde to M tilde. And the inverse monodromy map is from M tilde to A tilde. So in other words, we are working with the second version of the monodromy map here. And by some reason, it's more. So let's see. This next slide is a bit of a technicality again, which is required for the rest. So let's introduce this quadratic Poisson algebra just for 1G. I don't have any index here, right? I take just matrix G and another matrix G, and this 1, 2 means that I take the tensor product of two spaces and compute the Poisson bracket between each matrix element of this with each matrix element of this. And the result is given by its quadratic bracket defined by the dynamical R matrix. In general, this is the simplest example of dynamical R matrix. The theory was pretty much developed by Tinkoff. But this bracket, and of course, you see what's important here is that L's have the bracket with G's. So eigenvectors have a bracket with eigenvalues. Eigenvalues have bracket, non-trivial bracket with eigenvectors. And the bracket is given by the Casimir. Right? Omega is constant. So this bracket is linear, this bracket is quadratic. The example of this bracket we saw in very old, well, 30 years old paper by Alexeyev and Fadeev in 2x2, right? Derived from conformal field theory. We got this bracket by just straightforward inversion of the symplectic form, which we got for the Schlesinger equation. But I'm going to discuss that on the next slide. So what's important is that this quadratic bracket can be inverted. And what you get is a symplectic form like that. Without this term, that would be the Kirillov constant. With this term, and Kirillov constant is degenerate. L's are Casimirs there. No, Kirillov constant Poisson bracket is degenerate form, of course, on the symplectic leaf. But if I add this term, then I get the non-degenerate form on the whole space, right? Space of pairs, G's and L's. And what's important here is that if I cook this combination, if I go back to my original A's, the matrix whose eigenvalues are L's and eigenvectors are G's, then it satisfies the regular Kirillov constant, the linear bracket. So this thing satisfies linear bracket, but the eigenvalues and eigenvectors satisfy the quadratic bracket. So that's an interesting technicality. I'm not sure it was completely known, right, to people. And the inversion of this Poisson bracket is the Kirillov constant symplectic form on the leaf. Okay, so keeping in mind this technical slide, let's just go further a little bit. Monodromy symplectomorphism. So there is this theorem that if I define, say, on a symplectic leaf, the theorem which was independently proved in '96 by three groups, by Hitchin, which was one group, and Alexeyev Malkin was another, and Henning Samtleben and myself was the third, is that if you assume that on the space of potentials there is this Kirillov constant bracket localized at each vertex, then you get the monodromy map gives you, gives you the symplectic, gives you the Goldman Poisson bracket on the character variety. So that was the. Now we got a little bit refined version of that. Namely, if you assume this Poisson bracket on the space of eigenvalues and eigenvectors of matrices A, the quadratic bracket, then on the character variety, you get the Poisson bracket corresponding to this symplectic form. So the extension of that old theorem to the extended space also holds, right? And Phil Bolsh told us after we have submitted the initial version that on the level of the symplectic forms, he proved it in 2010, which is probably correct, but the formalisms are very different, so it's a bit hard to compare. Anyway, so this is this old symplectomorphism, which was proved long ago, and yeah, that was 27. So the extension to the this eigenvalues and eigenvector spaces. Okay, so now it turns out that if you add these t variables to the picture, then this relation holds for fixed t's. If you add t's to the picture, then you should naturally add this term to the relation between forms, right? And these h's are the canonical Jimbo-Miwa Hamiltonians. And essentially this statement is, well, some indications that this kind of statement is correct were given by Itzlisov-Prokhorov like 4 years ago, and they stated a conjecture about the relationship of their formulas to Goldman bracket and its extension, and we kind of refined this conjecture and proved it. And what's the main tool to deal with that? Well, it's this so-called Malgrange form, which was extensively used by Marker like over the last 10 years. Now, the interesting thing which I want to attract your attention to is, well, symplectic Hamiltonian formalism for the regular Schlesinger system, which looks like that in terms of A's. And for Schlesinger system, which you write in terms of eigenvectors, which looks like that. Yeah? Originally, so from isomonodromic condition, you get this system, and that of course implies the system for A's. And for system in terms of A's, you have Kirillov constant bracket, and you have the Hamiltonians given by Jimbo and Miwa. So what replaces this for that version of Schlesinger system? Of course, the natural version of it is just a second, where, yeah, I don't think I have written it explicitly. So the theorem is that for this form of the Schlesinger equations, the natural bracket in terms of G's is this quadratic bracket in terms of dynamical matrix, and Hamiltonians are the same, the good old Jimbo-Miwa Hamiltonians. Okay, so let's get back to the tau function. So the tau function, originally, the definition of tau function was like that. D log tau, but dtj is h. But our definition is, well, so our goal is to say, how tau depends on monodromies. For that, we do the following. We choose some symplectic potential on the LG side, on the space of coefficients of my equation, and we choose another symplectic potential on the character variety. And that symplectic potential on character variety we use using Fock-Goncharov coordinates. And then, in addition to these equations for tau function with respect to t variables, we get natural equation for the tau function dependence on tau function on monodromy variables, which looks like that. So here we take g's, differentiate them in terms of with monodromies. It's natural to assume that, well, if the natural definition would be without that term, but that's of course wrong, because then the form here wouldn't be closed, right? So you couldn't integrate it. So you have to subtract this counter term, and then you get the closed term with respect to monodromies, and you can integrate. And this is, so if you do that, then you realize, using this the logarithm conditions that say if you change the triangulation, right, then tau function transforms using the logarithm. Again, people were observing this the logarithm in the transformation of tau function for a long time, and here is the meaning of that. And everything is particularly straightforward if you are dealing with real character variety. On complex, there is this business about the branches and so on. And again, SL2 case is much easier than everything else. Then say if I take this, so here there are some subtleties, because in this formalism, originally if you apply this literally, you get that the tau function also depends on normalization of the eigenvectors of monodromies. But you can define a partner of it which is independent by this multiplying with the simple exponent, which is a combination of eigenvalues and these normalization factors. And then this thing is already depending only on t's and monodromies. And then say, if you want to differentiate it with respect to the Fock-Goncharov coordinate, you have this very simple formula, and the counter term is really easy, right? If this HE connects vertices V1 and V2, then we have this main term where G's should be differentiated with respect to zetas, and the counter term is pretty easy. It's just sum of zeta variables corresponding to vertex V1 minus sum of zeta variables corresponding to the second vertex. And again, if you flip the edge of the triangulation, the tau function transforms in this easy way, right? So it's kind of naturally, you may try to interpret it as a section of the logarithm line bundle, which is not as direct as we would like it to be, because say if the 5-term co-cycle condition depends on the choice of branches, and in the real case it's easy. In complex case there is quite some pain there. Now, say here this slide is pretty technical. I want to show here that you can efficiently write how these eigenvectors of matrices A depend on zeta variables, on Fock-Goncharov variables. So the equation looks a little bit non-local, right? In contrast to the usual Schlesinger system, there is this integral, and this integral involves the psi function, right? The psi minus means just psi function on one side of the edge. So you put it here, so that, and well, there is this non-local term. So it's a little bit well, but it's still rather precise. Now, with respect to the tau function, again, the explicit formula for its logarithmic derivative in zeta variables looks like that. You have this. Okay, so that is one part of the story. Now, how to use this formalism to talk about WKB expansion. Right? And first, I have like 12 minutes left, so I'm going to maybe a couple of minutes more, and that should be enough to cover the remaining 8 transparencies. So examples of WKB, I'm going to give 2 examples. One example is this original Rosley-Nekrasov-Shatashvili case. And this is the second order equation on the Riemann surface with n punctures. And the potential here is not, naively it would be quadratic differential, but it's not. It's a projective connection. So difference of 2 projective connections is the quadratic differential. So we write this potential as some reference projective connection, SB, which is called the Bergman projective connection. It can be written explicitly in terms of theta functions, and the quadratic differential with n poles, and the residues are fixed. Now, the whole structure here, if you want to talk about WKB, you do the following. First, you introduce the coordinates on the space. The space, moduli space here is a space of pairs, the Riemann surface quadratic differential. So you introduce a canonical cover corresponding to this guy, v square equals q. This is the 2-sheeted cover of the original Riemann surface. Here are some dimensions. You take the homology space of this cover and decompose it into plus or minus part according to the parity with respect to the natural involution. And you choose in H minus, and it's called the prim space, right? You introduce the periods of V, because V is antisymmetric under the involution, so its periods are non-trivial only along A minus and B minus cycles. And the natural symplectic structure on the space of potentials here is like that in terms of the homological coordinates. Now, if you look at the monodromy map of this equation, right, and here we are talking about PSL2 monodromies to avoid various technicalities. Then on the monodromy map, but PSL2C. On the monodromy map, you can write the Goldman bracket on the character variety. You can write the Goldman bracket in terms of alpha and beta extension of Fock-Goncharov variables. So by linear combination of the usual Fock-Goncharov coordinates, you can cook the actual Darboux coordinates for the Goldman bracket on the symplectic leaf, and then you can prove the theorem. And the proof repeats the proof of our paper with Mark and Haya Norton, like 4 years ago, 5 years ago, that this map is symplectic between this bracket on the coefficient side and, well, this form on the coefficient side and this form on the character variety. The proof here is one line, but the proof is pretty technical, I must say. And then the Yang-Yang function by Nekrasov-Rosley-Shatashvili is the following. You pick some symplectic potential on the coefficient side, pick some symplectic potential on Goldman side, on the character variety side. And this F is the monodromy map, so you take the pullback of Goldman potential with respect to the monodromy map, subtract this, and you get the generating function. So what you can do with that, how you can study it. You can't compute it, of course, it's impossible. You can say in some cases, you can think of that as a section maybe of some line bundle. In the real case, it could be the D logarithm. But what you can do explicitly is to study its formal WKB limit. And it turns out that if you just rescale this quadratic differential part, you can't rescale this because tensorial properties will get spoiled. Then you do this standard WKB expansion, you get this Riccati, this S, these relations from the Riccati equations, and you get a bunch of meromorphic differentials on your canonical cover. So the first differential is this V, the second is 0 actually. Well, this is important. And V1 you write in terms of Bergman connection minus the Schwarzian derivative of the Abelian integral of V with respect to any local coordinate. So this is meromorphic, and all others also meromorphic. And then you can integrate them. For each cycle, they are all odd with respect to the natural involution. You can integrate them over all cycles in H minus. What you get is what is called these periods called Voros symbols. And then, well, what you do, I'm going to describe it briefly here. This differential V defines the critical graph. The critical graph is the following. You take Abelian integral of V and take the family of curves, imaginary part of this is 0. Right? And these curves typically connect poles with zeros, poles of V with zeros of V. And this is this blue graph here. X is a 0 of V, Z is a pole. Right? So this blue graph, and from that you cook two other graphs. One is the graph connecting Z's, and that's going to be the original triangulation from which we cook Fock-Goncharov coordinates. And another graph are these zigzag lines, which turn out to be actually the branch cuts on the canonical cover. And so this is, and then to talk about WKB expansion of the generating function, we have to look at the WKB expansion of symplectic potentials. And the symplectic potential on the monodromy side is written in terms of Fock-Goncharov coordinates. So how are they, what are their H-bar expansion? And here we have this formula, which is inspired by, in principle, people were guessing that this formula is correct for a long time in various contexts. Most recently, it was proved in the papers by Allegretti and Bridgeland. We had to do it more or less independently because, strictly speaking, in our context, it was not known. But still, this kind of expansion seems to be correct and proved. And then once you have it, so essentially the Fock-Goncharov coordinates and the H-bar expansion you write in terms of periods on the Riemann surface, which is a highly non-trivial fact if you think about it. And then you define, well, it turns out that prepotential for this kind of form, the A's and A1 and B1 are periods of this guy, and B's and A's are periods of this guy. It was known before. It was studied in our papers with Alexei Kokotov for quite a while. And the solution of this has the meaning of determinant of D-bar operator. Or, well, has this interpretation. And then playing with all those objects, you get this theorem for W expansion of G. So you can compute the leading term. H-bar term is 0, and the leading term is essentially the determinant of D-bar operator plus a little bit of some defect, which is the coupling of V1 and V minus 1. And the coupling comes from this Riemann bilinear identities. And I think that statement is pretty non-trivial, right? That we know the leading term of the Yang-Yang function. And another example is this WKB expansion of this Fuchsian system. And this thing is not yet published. This is the content of our joint work with Marco and Fabrizio. So here I have renamed the residues. And you see we have here 1 over H-bar expansion. And in this context, I can't talk about isomonodromic tau function, but by reason because in this form, the equation doesn't admit the isomonodromic deformations. But still, I can take the generating function of the monodromy map and see how its WKB expansion looks like. And here there are some details, right? The symplectic potential on the space of coefficients is this Kirillov constant thing. On the monodromy manifold, it's defined in terms of Fock-Goncharov coordinates, and so on and so on. And you see why this case is more difficult, because on the Riemann surface, what I was describing, I didn't have this middle term. 1 over h bar term was absent, which simplified the formalism a lot. Here we have various extra terms. We have 3 first differentials. Well, V0 is non-trivial, it was trivial before. V1 is much more difficult than it was before. Before we didn't have this term. And anyway, so the message is that one can efficiently integrate and find the first 3 terms. And all of them must have some independent meaning, which we didn't quite understand yet. But they should be important. In particular, this G-1 term is the only term where the monodromy side is talking to the coefficient side. And in particular, it involves the antiderivative of the vector of Riemann constants on the moduli space, right? And here I am like summarizing some answers just to give you an idea of what's going on. There are various regularized integrals of V's. And there should be, we suspect that there should be a lot of interesting structure along that, around these objects. In particular, there should be a clear link to the topological recursion. And also, all these, we know G-2, G-1, and G0. But the most interesting thing is the next term, which so far we can't control, because that would be what is called the Joyce function. This object and its generalization to the higher genus would be the Joyce function by Bridgeland and company, from which they developed the theory completely parallel to the theory of Frobenius manifolds, and which is pertinent to various structures which are important both mathematically and physically. But this part of the work is still a little bit incomplete, so I think I stop here, and I think it's time anyway. So thanks for the attention. Yeah?
Thank you. So I'm gonna take questions from the audience. If anyone has questions. You can ask naive questions, because
yeah,
I'm definitely no expert on this, but it does ring a bell to a few. Or is there someone else talking? Or
if I may ask a question.
Yeah, please. I can ask my questions.
So hi, Dima. Nice talk. I enjoyed the talk. So when you mentioned the relation between the Fock-Goncharov coordinates and the periods, I was wondering, there's of course a basic issue usually. You mentioned several times that you need to choose the symplectic potential on the side of character variety, because I mean, one issue with the Fock-Goncharov coordinates typically is that there's no natural polarization in them. I mean, there can be, say, for the same triangulation, several different choices of a symplectic potential. Yeah. Whereas then when you have periods, of course, you must have somehow well, typically, I mean, at least typically what one does is to choose then a polarization by choosing a canonical homology basis. So how does it work then? So is it that basically the choice of a canonical homology basis would then imply or would naturally induce canonical polarization on the level of the Fock-Goncharofs? Is this the way it works?
Yeah. So of course I have swiped many things under the carpet in this talk. And you are just asking me to lift the carpet a little bit. And so let's look at this formula, right? This is the Goldman symplectic form on a leaf, and here I'm writing like the Darboux extensions of Fock-Goncharov coordinates. So what we do here is the following: if we take this, let me see, where was my picture for this graph, right? Just a second. Let me talk about the graph first. Yeah. Okay. So we look at the critical graph of the differential. Now we have the canonical cover. The question is how to connect the zeros by branch cuts, because we can connect them in many different ways and we can get different covers. Some of them are going to be equivalent to canonical cover, some of them not. Right? Now it turns out that this cover, which we get just choosing the branch cuts along the zigzags, is conformally equivalent to the canonical cover, v square equals q. Right? It's a non-trivial statement, and well, not completely trivial, at least. So the question is why, right? But this seems to be the case. Now, you can naturally associate, if you look at the brackets between Fock-Goncharovs, then if you associate Fock-Goncharov coordinate to this edge and to this edge, then the bracket is exactly up to 1 over 4 is the intersection index of this cycle in H minus and this cycle in H minus. So you have this homological interpretation of the brackets between the regular Fock-Goncharovs. And then you say, aha, now I can make the map from, and of course, the set of Fock-Goncharov coordinates is excessive, right? Because the number of these guys is greater than the dimension of the symplectic leaf. So you have to make some choices anyway. But you say now, okay, now I can extend by linearity my Fock-Goncharov coordinates to the whole H minus. I can label Fock-Goncharov coordinates by elements of H minus. And then I can take in H minus, I can take the symplectic basis and say, okay, now I assign Fock-Goncharov coordinate to A minus cycles, right? And B minus cycles. And these are going to be the honest Darboux. And then the choice of symplectic potential is you can take zeta B d zeta A or minus zeta A d zeta B. We prefer to antisymmetrize, just not to give any preference to N or B cycles. But the critical observation here is that if you look at the standard bracket, the Goldman bracket between Fock-Goncharov, it has this easy homological interpretation, right? It's just the intersection index of the corresponding cycles in H minus. I don't know. Probably we were a little bit learning the subject when we were writing those. So definitely there is a lot in the folklore. When you talk to Fock, for example, then well, he would tell you that, yeah, we knew that, we didn't publish, we knew this, we didn't publish. For us, it was all new, so we published everything we learned. And I must say, we had to learn it in a hard way, because when you ask Volodya Fock, he kind of understands everything, but it's not always easy to extract it from him. So nothing comes for free in this business.
Yeah. Okay. But in the end of the day, sort of, you would agree that yeah, you are making a choice, but yes, it is the choice of the canonical homology basis, which then say can be carried over to the choice of a polarization on the Fock-Goncharovs.
Right, right,
Yeah.
right. It's you see, if you are dealing with this WKB business, then at least you have this God-given triangulation which comes from critical trajectories.
Mm-hmm.
If you don't do WKB, if you're just having this the symplectomorphism between two complex manifolds, then the triangulation is not God-given. And you don't only change the canonical basis in on the cover, you also have many different covers. And you have to say how you jump from one triangulation to another. And here you get these logarithms. But again, the nice co-cycle condition you have in the real case, once you start getting to the complex case, it's getting a bit unclear what you, but then of course you have this transformation which you were writing in your paper, that if you look at the symplectic potential, for example, I don't know, here, right? Then, okay, zetas are logarithms. So if you shift logarithm by 2 pi I, then the point of on the character variety doesn't move. And what you got on the coefficient side also doesn't move. So it's pure transformation of but the potential changes, right? So you get some kind of line bundle, so to say, but it's not really, because there are other transformations. So you should glue somehow, if you want to do it in the complex world properly, you should glue all those transformations together and check that you get indeed some well-defined line bundle. Again, I spoke to Goncharov. He said, yeah, we know how to do it. It's written in our paper with Fock. And then you open and, well, maybe it is, but it's in a foreign language to me. And then you ask him, anyway, so that's, I'm trying to explain all that in a pedestrian way, and it's not always easy to find a common language with other players in the field.
Okay, yeah, thanks a lot.
Yes.
Thanks a lot. I mean, yeah, we should continue discussion, but that, of
Yeah,
course,
yeah,
some other time.
it would be nice, yeah, to have more detailed discussion, because I think there are many points, many subtle points here, and I can just do it I browse through over very quickly. I have put many things into these 34 slides. Check. In particular, it would be nice to see how how you came to these relations, because for us it comes from the construction. I wouldn't be able to figure out that, okay, from scratch, why you should have these periodicity equations which you had, right? Here it's come. I don't see the philosophical foundation.
Okay, yeah, I didn't want to hijack the discussion, but just as you're bringing it up, I mean, one word, it was basically simply that we were coming from this, by now, I think it's typically called these Kiev formulae, which from the, say, motivations we were interested in was, well, I think becoming clear that this is a key role, a key feature. And if you have these, say, what you could call generalized theta series expansions of tau functions that then bring into the game the conformal blocks and so on. Well, then basically these structures come very naturally and basically automatically, because yeah, you have I mean, these Kiev type expansions that Lissovy and collaborators discovered, they imply these two types of periodicities of the tau function basically immediately, and then you just start asking how does this transform from, say, coordinate system to coordinate system, and the whole structure sort of unfolds. That is in essence sort of the main ideas. But yeah, this Kiev formula is sort of then automatically leading to a difference version of the story that you told. And yeah, now sort of you're giving the first hints as to how the difference and the differential versions should relate. So, but I think this is indeed a very interesting point to really clarify to the end.
Is it true that they essentially worked in Fenchel-Nielsen, right? So the main coordinate.
Yeah. I mean, right. So this was, in some sense, I think, perhaps one of the new ideas. I mean, of course, all that was in the initial work of Lissovy and followers were using Fenchel-Nielsen type coordinates. In the end of the day, I think, and first examples were also in the paper, say for Pont-Levé 3 in the paper with Itz Lissovy. So, well, they didn't really discuss the geometric nature of the coordinates, but they had a weak and a strong coupling expansion. So for Pont-Levé 3, you realize you have I mean, you're on the two punctured sphere with irregular singularities, and they had two systems of coordinates adapted to weak and strong coupling expansions respectively. I think that what they did not notice is that the so-called strong coupling expansion coordinates are actually Fock-Goncharovs, whereas the weak coupling coordinates are the Fenchel-Nielsens, and they're related by one of these symplectomorphisms that well, sort of form the basis of our proposal.
Mm-hmm. Oh, Jörg, so thanks a lot. It would be nice to
yeah, sorry,
because
you sort of forced me. I didn't want to hijack the discussion here, but
you will have to explain.
Yeah, we should discuss
scratch, right from the very beginning.
Yeah. Thanks again. So
yeah, thank you.
So since it's 4:45 and the discussion was hijacked by the previous question, I'm just kidding. I think we should just thank the speaker, and if people have other questions, they can ask them, but in case some people have to go. So thank you, Professor Korotkin, for a very nice talk.
Thank you very much. It was my pleasure.
And
thank you very much for attending.
Yep.
Okay, see you guys.
Yep.
Bye.